Hello everyone, this is Dr. Fan. We're learning work and energy. The physics of walking is rarely discussed in the physics classroom. And as a matter of fact, many physics teachers themselves, they do not understand the physics of walking. And in order to solve this problem, let's discuss it today. These are some snapshots for a walking person. So the person has one foot in contact with the ground. So this foot pushes the ground, and as a reaction force, the ground pushes this person forward. So this is a static friction force. Initially, the person has a velocity of 0, and after pushing the ground, the whole body of the person is moving forward and gains a velocity of v. So in order to solve or understand the work and energy, one equation naturally comes into our mind, which is this equation, work-energy theorem. The net work done to the system equals to the change of the kinetic energy. And if we consider the person is our system, the final kinetic energy of the person is half mv squared. And the initial kinetic energy of the person is 0. So the change of kinetic energy is half mv squared. So now how about the net work done to the person? We know for mechanical work, it equals to force times displacement times cosine theta. In order to do work, not only you should apply a force, but also the force application point should have a displacement, and the angle between the force and the displacement also affects the work. So if we look at this person right here, this person is under friction, but also the ground give a normal force. And also gravity applies onto the person on the center of mass of the person. So the person is under 3 force. Let's first look at the work done by gravity. So initially, the person's center of mass is right above his foot. But because the ground is pushing this person, so the person, his overall body is moving forward. So let's see, this is the center of mass of the person afterwards. So his initial center of mass point is right here. So the center of mass actually has a displacement. Let's call it x. So now, if we look at the work done by gravity, it equals to gravity times the displacement, which is x right here, and then times cosine theta. But we know gravity is going down and the displacement is horizontal. So the angle is 90, so times cosine 90, which equals to 0. In other words, gravity does not do work. Then let's look at the work done by normal force. Normal force is applied by the ground, but we know this contact point does not move. In other words, the force application point of normal force would not have any displacement. So even though we have normal force, but because the displacement is 0, so normal force does not do work. Similarly, the static friction force also does no work. Why? Because the static friction force is pushing this person forward, but this contact point does not move. Otherwise, the person would sleep. So although we have static friction force going to the right, but this force application point is always in contact with the ground, which has a displacement of 0. So static friction force also have 0 work. So now we look at the net external work, which equals to all this work added together, which equals to 0. But we know the change of kinetic energy equals to half mv squared. So clearly, the net external work does not equals to the change of kinetic energy. Does this mean the work-energy theorem is wrong? So what's the issue here? Let's look at this question from a different perspective, then we're going to revisit this work and energy theorem. If we do a free body diagram on this person, this is what we got. We have gravity going down, we have normal force going up. We also have static friction force going to the right. And for free body diagram, we consider all the forces applied onto a dot. But what is this dot right here? This dot right here is actually the center of mass of the person. So what is the center of mass? Center of the mass is a point where all the masses are concentrated. So when we use free body diagram and Newton's second law, we actually assume all the forces apply onto the center of mass. So if we write down the Newton's second law, along the x direction we get Ff, only the static friction force. Along the y direction, sigma Fy equals to normal force minus Fg. If we assume the person is not moving up and down, so the net external force along the y direction is 0. Then this person is only under static friction force, and this static friction force equals to mass times acceleration. But because all these forces are applied onto the center of mass, so this acceleration should be our center of mass acceleration. So how this equation will help us to understand work and energy. Since this force is a constant force, so this motion is a constant acceleration. We know from kinematics V final square equals to V initial square plus 2 times the acceleration times the displacement. So our initial velocity is 0 and our final velocity is v. And we also know our acceleration from this equation. So 2 times the center of mass acceleration times the center of mass displacement. As we discussed before, originally the center of mass is right above the foot, but after a while the center of mass moves here. So this is the initial position of the center of mass, then the center of mass moves a displacement of x. So from this equation, we can get our center of mass acceleration. So our center of mass acceleration equals to v squared divided by 2 times the center of mass displacement. Now, if we have our center of mass acceleration, we can substitute into this equation. So we get F friction equals to mass times the center of mass acceleration, which is mass times v squared divided by 2 times the center of mass displacement. If we move the center of mass displacement onto the left, we get friction force times the center of mass displacement equals to half mv squared. Because everything is center of mass, so this velocity should also be center of mass velocity. So this is what we get. So if we look at this equation right here, on the right, we actually have the kinetic energy of the center of mass. On the left, we have something very similar to work, but we know the net work onto the system is 0. So what is this term? Physicists actually give this term a name, which is pseudo work. So this equation basically says pseudo work equals to the change of kinetic energy of the center of mass. Please pay attention. The velocity, acceleration, displacement we discussed here are all with respect to the center of mass, because for this person, different parts of the body move differently. For example, the center of mass may gain a velocity of v, but this contact point does not move at all, and other parts of the body may also move with a different velocity. So that's why this equation only applies to center of mass. And we got this, the pseudo work down to the center of mass equals to the change of kinetic energy of the center of mass. And this is very popularly used in biomechanics. Now we understand the situation a little bit better. Although the real mechanical work is zero, but there is a pseudo work to the center of mass, and as a result, the center of mass gains a velocity. Now let's go back to the big problem. Why the net external work done to the system does not equals to the change of kinetic energy. In other words, does work energy theorem work or not? Work energy theorem is valid, but there is a condition to apply work energy theorem. And when we use work energy theorem, we assume the object is either a point mass or it is a rigid body without no internal energy. And this assumption is completely wrong for a walking person. First, the person is not a point mass or rigid body. Clearly, different parts of the person move differently, and the contact point never moves. But also, the person has a lot of internal energy. The person has heat, right? We have our body temperature. Also, we have muscles, tendons, and a lot of moving parts. So a person clearly has internal energy and clearly is not a point mass. As a result, for a walking person, we cannot use the work energy theorem. Instead, we can use the conservation of energy. So we know the conservation of energy is the change of energy to the system, which we consider the person as our system, equals to the net external work done to the system. And we know the total work done to the person is zero. And we also know in this case, the person's energy has kinetic energy. So we have the change of kinetic energy, but also we have the change of internal energy. Because we know the change of kinetic energy is a positive, which is half mv squared. That means the change of internal energy is minus half mv squared. In other words, the internal energy of the person is decreasing, which makes sense because whenever you are walking, you clearly consumes your internal energy. And this internal energy is consumed mainly by using your ATP molecules. That's why whenever we are walking, after a while, we feel tired or hungry. Now you can see that walking still obeys the physics law, but you cannot use work energy theorem because the person is not a point mass and the person has internal energy. But we can use the conservation of energy law, and this law shows the reason the person gains kinetic energy because the internal energy was consumed. So there is a conversion of internal energy to kinetic energy. I hope our discussion today clarifies the concept, and I hope now you understand the physics of walking. Thank you for your attention. I will see you next time.